So this raises some profound questions about the usefulness of machine learning, right? What is this? What is all this brouhaha about, right? Why is machine learning so important, right? If you could just be flipping coins, okay? What does this really mean for you? Well, remember Ross Quinlan, the inventor of decision trees and the FOIL first order learner and whatnot, right? One of the most famous, most widely cited people in machine learning, and the UW alumni, right? He did his PhD here. I remember him giving, a keynote talk at ICML, for one of the top machine learning conferences, where somebody, this was at the time that these results came out, and somebody told him, but aren't you worried about the no free lunch theorems, right? Don't they make all of this useless? And, Ross is like this very calm and flappable guy, and he looked at, at the person and said, like, well, no. The no free lunch theorems are like the death of the solar system. It's going to happen someday in the distant future, but in the meantime, you can live your life and not worry about it. And luckily for us, he was right. Now, why was he right? So, now this is my next question to you: is why does this not? Here's the theorem, right? Why does this not imply that machine learning is useless?
Not all concepts are equally useful. For example.
Exactly. Yeah, absolutely. Notice this thing here, that I'm doing an average, right, over all possible concepts, where they all have the same weight. Right? It's 1 over the size of curly f. Right? But in the real world, not all concepts are equally likely. Of course not. Very far from it. Right? The whole reason why we humans are able to learn in the real world and machine learning algorithms are able to learn in the real world is that the real world is not a function randomly selected from the set of all possible functions. Hell no. Right? And when you go to a new application of machine learning, there's always this pathological possibility that it's like something completely, out of left field. But most of the time it's not, because, the world does have regularities. And, in some sense, the power of machine learning comes from the fact that there are some very general regularities that our learners can exploit that are enough when combined with data to do quite well. And in a sense, our job, as developers of machine learning algorithms, is to try to develop algorithms that somehow encode those regularities and exploit them for learning. Okay?
Even if they weren't equally likely across the entire universe, would this still be the case that it's not the end of the world? Because it's not likely that you're going to pick if you randomly select your data, assuming that you can randomly select it, it doesn't seem likely that you'd ever get all of the data in your training set being F and all of your test data being F prime.
No, but
it seems really unlikely.
No.
I'm glad
you asked that question, right? There's a fallacy in your question, right? You're saying all the data. Remember, you're saying all the data in training is from F, and all the data in test is from F prime, right? What's wrong with this argument? The training data is neither from F nor from F prime. It's from both. Remember, the training data is the same for both. If, let's say you are now, applying machine learning to a new problem that you've never seen before. If that problem really was generated at random from the set of all possible problems, you would have no reason to believe that whatever your learner is would be good, would be better than flipping a coin. Even if your learner was a big stacked complication of decision trees and neural networks and everything in the universe, there would still be no reason to believe that that would be better than flipping a coin. So the usefulness of machine learning hinges completely on the fact that this is not a uniform distribution.
Okay.
And sometimes there are problems where nothing works and then you just give up, and we tend to not hear about those, but they do exist, so who knows, right? There's an amount of selection bias in that, we keep applying machine learning algorithms to the problems that they're successful in, to certain broader classes of problems, right? Maybe there's a lot of stuff out there in the world that we just think is random, right? But it's not that it's random, it's that our brains and our algorithms don't know how to figure out where the order in that is, right? For all we know, that's what's going on. But at the end of the day, what matters is, for any given problem that you're going to apply machine learning to, there's a very good chance, based on past experience, that, the assumption of some or other of your classifiers will actually be a reasonable match for that problem. Okay? Nevertheless, it remains the case that you should not expect one learner to always be better. Right? Because remember, a learner is better if it's more correct, if it encodes correctly more truth about the domain. Right? The more your learner already knows about the domain in whatever form, the better off you are, right? But the more it knows about one domain, the less it knows about a different domain, right? So there's no learner that's always going to be better for all domains, right? A learner might be better in a certain class of domains that share certain structure that learner captures, but then there's another class where another learner will do better, right? So you can't say a priori like, people used to circa, 1990, oh, backprop is always going to be better. I mean, people first found out empirically that wasn't the case, and then they started trying to figure out why. And that's when, it's not an accident of history that, the no-free-lunch theorems and things like bias variance came along at that point. Because first people were developing these algorithms pretty much in isolation, testing them on different things and believing in them. And then they started comparing them head to head. And then they found out that no algorithm always won. And then they tried to figure out why, and that's when things like, no free lunch and bias invariance came up. Okay? So the moral of the story for you, and this is a very important moral of the story, is do not have a hammer that you want to, hammer, everything with, irrespective of whether it's a nail or not. A good machine learner doesn't have one algorithm. It has a suite of algorithms and will apply them and the different variations of them. Right? You need to have a toolkit, not just one tool. Okay? Even today, there's still a lot of people who fall into this trap of, yes, they really like decision trees and that's what they use all the time. That's a dangerous thing to do. This is much less common than, in the early days of data mining, there were like single algorithm systems being put out, like, like Quinlan's system. These days, every company worth its salt, provides a suite of algorithms, right? But, it still behooves you to know how to use them and try them out and whatnot, okay? You have to go through this process of trying things, trying variations of the data, understanding the problem before you actually get something that's really good, okay? So that's one moral of the story. But now let's, maybe there's something here that remains a little bit puzzling, which is the following. Or maybe not, right, with what you know already. So it's one thing to say, well, decision trees are never better than neural networks, or vice versa, right? Well, they're very different, right? But what about a one-layer perceptron, right? Think about neural networks, right, which we were talking about last time, right? What about a one-layer perceptron and a multi-layer perceptron, right? We are claiming here that it is not the case that the multi-layer perceptron is always better than the one neural perceptron, right? How could that be the case? Anything that the one hyperplane perceptron can learn, right? The multi-layer perceptron can learn too, right? It could always, blow away the weights of all the other, neurons and just leave one, right? And there's for sure a lot of things that the multi-layer perceptron can learn that the one-layer perceptron cannot, right? So the question is, how do you square that with the fact that neither of them is always better, right? How come the multi-layer perceptron isn't always better than the single-layer one? Any ideas?
The more complicated one might hallucinate more.
Might what?
Hallucinate more.
Yeah, absolutely, right? Overfitting. Right? I told you the answer is always going to be overfitting, and this is no exception, right? That's the thing, right? Again, this is something that people did not appreciate in the early days of machine learning. In the early days of machine learning, people were like, oh, we need to build ever more powerful learners. We need to go from, perceptron to multi-layer perceptron and from single rules to rule sets and whatnot, because the more powerful, the better, right? We want to be able to learn more things. What they didn't quite realize is that there's a downside to being more powerful, which is exactly, your word is the right one, is you're more prone to hallucination, right? You're very creative, you could be a genius or you could be a madman. So the problem, with the multi-layer perceptron over a one-layer perceptron is that it's more prone to overfitting. Yes, it can learn things that the one-layer perceptron can't, but it's also more liable to basically crash and flail and produce silly things when, the perceptron is very boring but also very stable, right? Things like perceptrons and naive Bayes, they're kind of boring, but on the other hand, they're safe, right? They're very predictable. They don't get, overexcited about patterns that they found here and there in space. It's like, I think there's a hyperplane here that separates my data. This is all I'm going to tell you. You might miss out on a lot of things. On the other hand, if you learn a decision tree and don't prune it properly, this thing could find all sorts of crap flying around. Okay? So what we would like to have is a way of understanding this trade-off. Right? This is the key. At the end of the day, when you're doing machine learning, you have to trade off the expressiveness of your learner, right? You want a very powerful representation on the one hand, but on the other hand, you don't want to, wind up hallucinating things. And this is a very big risk in machine learning and data mining, is hallucinating things. In fact, I don't know if you guys know this, but data mining first appeared in the 1960s as a pejorative term for hallucinating patterns. Statisticians used to call data mining what you should not do. Now, if you were finding patterns where they weren't, and they say like, oh, you're just data mining, also known as torturing the data until it confesses. Right? You always have to be aware of doing that. And, these days, data mining is just, has gotten beyond that, but that danger is still there. So let's